Okay, so in this lab session, I will do mainly two things. Number one, I will implement the entangling circuit, the circuit that can be used to prepare entangled states. And I will also describe another visualization scheme, which is called a Qsphere. Uh, and Qsphere is actually in addition to the block sphere. The block sphere is useful, really speaking, only for a single qubit system. Or if you want to represent a multi-qubit state, you can faithfully represent it on multiple block spheres, one block sphere for each qubit, only if those states are unentangled. Because when states are entangled, you can't really think of as a state of one qubit and a state of another qubit and so on, and you have a block sphere for each qubit. So you need another scheme, and that's what Qiskit people have devised. They have devised a Qsphere that jointly represents the states of qubits. I will, show that, and then I will present a small circuit that represent how we can implement different functions, in phases, as I was talking towards the end, using phase kickback. Okay, so let me share my screen. So let's start Jupyter. Okay, let me start with a fresh notebook. Perfect. So now let's import a few things from Qiskit. So let's import quantum circuit, and today we will be doing some visualization. So from Qiskit, let's Qiskit visualization module. Let's import plot state Qsphere. This is the Qsphere that I was talking about, and we will also be doing some histogram plotting. So let me import that as well. Okay, so Qiskit VU. Okay, there's A missing here. Visualization plot state. Oh, there's a comma missing here. Okay, perfect. And also from Qiskit quantum info, let's import state vector that we will use to evolve state vectors. Okay, so let me first prepare, let me call it some my circuit, and I will first prepare an entangling circuit. So it needs 2 qubits. Okay, and it's a simple circuit. I only need a Hadamard gate on the first qubit, and I need now a new gate. It's control NOT gate, control CX, and I will have to specify the control bit. Control bit is coming, it is 0, and the target bit comes later, so it's 1. Let's draw this circuit using matplotlib library MPL. Perfect. So this is the circuit that we have. Okay, and as I discussed in the last session, that Qiskit by default initializes all the qubits in 0 state. So if I evolve it, it will evolve from 0 state. So if I want to work out the output for some other state, I will have to use that state. So let's define a state vector from label. So let's use some 1-0 state. Okay, so okay, SV is equal to state vector, wrong spellings. Okay, perfect. And now we can represent this on Qsphere by using plot state on Qsphere SV dot data. So this takes the data from the SV vector and plots it on this thing. So let me show how to interpret this Qsphere, and the interpretation happens like this. So what it does, now you see the let's say there is some state psi 0 0 plus 1 1 and so on. So what it does, that if you have a 2-qubit system, so the 0 0 is over here and the 1 1 state is over here, and the state which is 0 1 or 1 0, it's described on this equatorial plane, that okay, there's this one point represents 0 1 and this point represents 1 0. So what it does, that if there are like this, whatever the eigenstates present, it puts a big dot over there. So for this state there's a 0 0 present and then there is a 1 1 present, so it puts a dot. Now if the amplitudes of both of these states is same, the size of the dot is going to be the same. If the amplitude, for example, this has 2 and this has 1, then this would be a bigger dot and this would be a smaller dot. So the size of the dot shows the relative amplitude of that state. But that's not all. It also tells us the phase. So if there is minus sign or some exponential iota something, so it changes the color of the state, and the color scheme is already provided here. For example, the red is the 0 state. We can see right from here. So red is 0 phase, green, yellowish green pi by 2, and then blue pi, and purple is 3 pi by 2. So the phase scheme is shown here. So the color of the this dot tells us the phase. So this is if you have a 2-state system. If you have talking about 3-state system, then this top dot represents 0 0 0 and the bottom dot represents 1 1 1, and then there is this there's this circle which represents states that have only 1 1. So one is 0 0 1, the other is 0 1 0, and the other is 1 0 0. And then the states with 2 1s are here. So 1 1 0, 1 0 1, and 0 1 1. So what the scheme is this: as you go down the bottom, the number of ones increases. So similarly, if there is a 4-qubit state, 0 0 0 0 is on top, 1 1 1 1 is bottom, and then there's a first circle on which you plot states with only a single one, and then the second circle you plot states with 2 1s, and then the third circle with states with 3 1s, and so on. So this is how the states are represented, and the key is the size of the dot gives amplitude and the color gives the phase. So this is how we can visualize multi-qubit states in Qiskit. So let me get back here. So this was the 1 0 state. So on Qsphere it's representing as a 1 0. Of course I can represent it on block sphere as well. For example, plot block multi-vector SV. Let's see what it. Okay, so I might be using wrong command. It's plot block. Oh, the B is small. Plot block Oh, multi-vectors. The spelling of vector are wrong.
Import नहीं किया होगा from Qsphere.
Sorry? Oh,
Import नहीं किया होगा.
I haven't imported the plot multivector, plot multivector. So this has to be imported. So from Qiskit visualization, import plot multivector. Now you see this is 1 0 state. So qubit 0 is in one state, and qubit the second qubit is in 0 state. And now you can also see how Python labels, how Qiskit labels these state. So the first 0, so the labeling is happening from the right side. The first bit on the right side is the qubit 0, and then qubit 1, then qubit 2, and so on. So it's labeling like this. So that's why this first 0 is coming on the qubit 0, and so on. So you see, this is an unentangled state, this 0 1, this 1 0 state. So I can plot it on Blocksphere, or I can plot it on Qsphere, no problem. Okay, let's now see what happens when this state passes through this circuit. So for that, we need to evolve this state. So let's say I have some new SV, and this is being obtained from the old SV state by evolving through my circuit. New SV, and this is quantum circuit. So state vector object has load. I think I have to import something else as well. And that is import state vector. We have already imported state vector.
So evolve is spelling.
Evolve is spelling.
Okay, evolve. Okay. Thank you. So this happens, when you do too much copying from around and do little typing. So after a while, you even forget this balance. Anyway, so let's print this new SV state. So you see, the state is 0. The first is 0, the second is 0, and then there is 0.7 and 0.7. 0.7, 0. So this essentially the state is 0 1 and 0 1. It's a combination of 0 1 0 1 because I'm getting the second and third element non-zero. So it's, and that's what it's a 1 0 state goes to that combination. So but now we also have to visualize it. Let's see if we can visualize it on Blocksphere first. So let me copy this command here, and this new SV. Okay, we don't see it on the Blocksphere using this, plot block multivector, because it's an entangled state and you can't really talk about the state of 1 qubit and the state of 2 qubit. However, if I plot it on Qsphere, SV, new SV, now I'm able to see. And you see, I have 0 1 and 1 0 state, and they are both red, which means it's a 0 1 plus 1 0 state, and they both have the same size, so their amplitude is also the same. Let's see if I start from state 1 1. This is 1 1. Now I get 0 1 and 1 zeros combination, but now 0 1 is with the phase pi, which means exponential iota pi, which is actually -1. So this is telling me that my state 1 1 after passing through this entangling circuit is 0 1, a combination of 1 0 and 0 1, with 0 1 is coming with a minus sign. Okay, let's now see how we can instead of discussing evolution of this circuit, let's say if we want to run it on a quantum computer, how the circuit should be defined and how we can do that. So for that, let me copy my circuit over here again, but now I'm going to add measurements to it as well. And for that, let me add 2 classical bits to this circuit. So now my circuit has 2 quantum bits and 2 classical bits. So my circuit, let me add a measurement. So the measurement in qubit 0 should go to classical bit 0, and measurement of quantum bit 1 should go to classical bit 1. And this is my new circuit now. It has these measurements added to it. Okay, let's see how we can simulate this circuit. Right now, I'm going to simulate it using a simulator, but almost the same code. The result would be similar as if the code is being run on a quantum computer. And that's what we are going to start doing from the next week. Okay, so or maybe we can start it from tomorrow. So tomorrow I'll try to run some circuits on IBM's quantum computer, and I will also show you where you should make your account and what information you should have before the next week. But today, let's simulate the circuit. So for simulation from Qiskit, let's import what is called air, and also execute the package that is used to execute this circuit, and also basic air. Basic air has some basic functionality that is actually not even available in air. Let's use for simulation, and let's set our simulator as from which is available in air package get backend. And the simulator that we are going to use is a COSP simulator provided by IBM in this Qiskit package. And this can, I think, simulate up to 32 qubits. So this has this advantage that if you are making a bigger circuit, then you can simulate it using this COSP simulator. So the command to simulate it execute with option that we have to specify the circuit that we want to simulate. So the circuit name is my circuit. So I'm giving my circuit as the first option to this command execute. And then I will need to specify my simulator. So you see this simulator is just a variable that is specifying the backend. So this time I'm using this COSP simulator. Next time we will see that if we want to use an IBM computer, we will essentially be using exactly the same command, but here we will be specifying that quantum computer. So that will be coming in simulator. So the simulator is specifying what computer we are going to use, and then how many times we are going to use this quantum simulator or quantum computer. So let's say we use it 1,000 times. So each time when we do measurement, our output collapses, to either of the state. But when we do simulation enough number of times, then we can get the statistics to show what would be the probabilities. So from this results, okay, so in this result variable, so this execute command has several things returning it in it. So let's take the results from this, and from the results, if right now we are just interested in the histogram, so get counts, and using the histogram, let's plot these counts. Here job object has no attribute results, so it's result. Okay, so now you see that since both of those, had an equal amplitude, after simulating, I see that probabilities for getting either state 0, 0 or 1, 1 state is half. Okay, so this is actually not running it for this input 1, 1. It's running it for inputs that are specified here. Okay, and the inputs that are specified actually in this circuit, they are 0, 0, because by default your qubits are initialized to 0, 0. So for 0, 0 input, the output is 0, 0 plus 1, 1. If you want to simulate it for, let's say, 1, 0, what you do, you can put an X gate on, let's say, your first qubit. So this is essentially equivalent to making your input as 1, 0, 0. So with 1, 0, and if we put the X gate on the second qubit, it's the output for 0, 1. And now we have for 0, 1 and 1, 0. Let's see what happens if we run it only once. I'm going to have a short equal to 1. Now you see, if short is equal to 1, I'm only going to get a single result. So this time the system, collapsed to 1, 0 state. Maybe next time it could collapse to 0, 1. Maybe 1, 0 again. So this time 0, 1. So that's why you need to have multiple runs, let's say 100,000, to get a good estimate of the probabilities of the of collapsing to different states, which are proportional to the amplitudes of these states. Okay, so any questions so far? All right, so if not, let me go to the second part where I'm going to work out that phase kickback that we were talking about, just to, as a practice, take another small circuit and see how we can implement those different functionalities. Because this is actually the part that will almost appear in almost every quantum algorithm that we will study later on. Okay, so let's take an example of phase kickback. Let me call it example PK. And this is some quantum circuit of n plus 1. And let me specify n over here, let's say 2. Now, there are several ways of doing it. The first thing is that I have to put the nth qubit in, minus state. So for that, the name is too long. Let me take it to be just EPK. I'll have to type it again and again. So this circuit, it's nth qubit, which is by default initialized to 0. That is what Qiskit always do. So if I have to turn it to minus state, I will first need to apply an X gate to make it 1. And then once it's made 1, let me apply a Hadamard gate, sorry, not on the 0th bit, but the nth bit, which is the last one. Now this will, turn my nth qubit to minus state. Okay. And let's apply
आप इसमें last qubit n plus 1 नहीं होगा rather than n?
No, the indexing starts from 0. So if n is equal to 2, I have a total of 3 qubits. The first 2 are the 0th and first qubit, and they will be acting as control. And the last qubit will be indexed as nth qubit. It's n plus first if you talk, in first, second, third. But if you talk in terms of index, its index is n.
Okay. Thank you.
Okay. So let's, apply a control gate with respect to the first qubit on the nth qubit. And let's say I don't do anything to the second qubit. And then suppose I draw this circuit with matplotlib. Let's see what we get. Okay, so this circuit, as you can see, the third qubit is initialized to minus state, and there's only one control X gate with respect to the first one, and this will implement one functionality. If you want to, let's say, do something with respect to Q1, you can do that. By the way, we can use a visualization aid. It's called a barrier. It does nothing, and it only puts these lines that can help us separate different parts of the circuit. So I can put a barrier here. Okay, so within this barrier, let me do something to the second qubit, and for that, let's first apply an X gate on this, and then apply a control X with respect to this on the nth qubit again, but I will have to apply the X gate again so that there's no CS gate. Okay, so you see, with respect to the second qubit, I'm doing an operation in sort of with respect, when this is 0, then this X gate will be applied, and when this is 1, this X will first make it 0, so this will not work. So this gate is being applied with respect to this Q0, and the second gate, second qubit is acting when it is 0. So with this, we can implement different functions. Let me, try to take a couple of examples. Suppose I have some state SV, state vector from label, and let's say, so since there are 3 qubits, so remember, this one has to be initialized to 0 because I'm now working with X, and then 0, and let's say this is 1 and this is 0. So always when you are reading, so this on the rightmost is one which is being applied to this Q0. Okay, so let's say, what is this SV vector? So you can see SV is 0, 0, 1, 0, 0, 0, 0, 0. Now, if I evolve new and make a new state through this circuit, it would be sv.evolve epk, and let's print this new state. Okay, now since this this last qubit is being in the minus state, I'm seeing some some of these things. So let me turn this last state back to 0. epk dot h on the nth. So to reverse it back to my 0 state, I first apply Hadamard, because Hadamard square is 1, and then I apply the X gate. Okay, so now this Q2 starts in 0 and ends in 0. So now okay, so now you see that when the input is 0, 1, your state vector is whatever it is, with a 1 coming at the third place, and your output is 0, 0, and 1 coming at third place. There's no minus sign. And can we see that that's what it should happen? If this is 0 and this is 1, of course nothing would happen, because the Q1 is 1. So first you apply X, it becomes 0, so nothing is being applied. But what if your input is 1, 1? So the first qubit is 1, the second is 1. So now you see the state vector is 1 coming at the fourth place, and the output is again the same, except that there's a minus sign in front of this 1. And now you can see that we can apply a negative sign two states of our choice. So half of them will be multiplied with the minus sign and half of them will be multiplied with the plus sign. And you can choose those halves by playing around, with this part. The key is to keep the target qubit in a minus state. Okay, any, questions? So I'll send you this notebook after the class. So let me download it as a notebook. Intro to Bell and is Kickback. Okay, so if there are no questions on this one, let me stop recording.